The following lecture is one of a series that covers the HNC Electrical Engineering Unit FY9E DC and AC Principles. In this lecture, we will be looking at the difference in the way power is consumed in resistive and reactive circuits. This slide provides a brief introduction to the presentation controls. Now the lecture has started, it will present each topic in turn and then stop, showing either the information icon or the note icon at the bottom right of the screen. The lecture may be restarted at this point by simply depressing the spacebar. Hovering the mouse over the lower portion of the video at any time will display the control bar. Click the control button at the end to enlarge the video to its full screen mode. Click the index button to display an index of all the topics covered in the lecture. Any of the available topics may be selected using the mouse or through the search facility. Finally, the volume control may be selected using the control button shown. Consider the following resistive circuit with a 3-volt AC supply and a load of 1.5 ohms. By Ohm's law, this circuit will draw a current of 2 amperes. And since the load is purely resistive, the current will be in phase with the supply. The power drawn from the supply at any point along the horizontal axis may be calculated by multiplying the instantaneous voltage by the instantaneous current. Between 0 degrees and 180 degrees, both the current and voltage are positive, so the resultant power consumed is positive and has a peak at 90 degrees. And between 180 degrees and 360 degrees, both the current and voltage are negative, so again the resultant power consumed is positive and also has a peak at 270 degrees. So, although the power is drawn in bursts from the supply, it is real power and capable of doing work. In this case, the energy drawn is being converted by the load into heat. Consider the following inductive circuit with a 3-volt AC supply and a load of 1.5 ohms. By Ohm's law, this circuit will draw a current of 2 amperes. And since the load is purely inductive, the current will lag the supply by 90 degrees. The power drawn from the supply at any point along the horizontal axis may be calculated by multiplying the instantaneous voltage by the instantaneous current. Between 0 degrees and 90 degrees, the current and voltage are positive, so the resultant power consumed is positive and has a peak value at 45 degrees. And between 90 degrees and 180 degrees, the voltage is positive, but the current is negative, so the resultant power consumed is negative, with a peak value at 135 degrees. In this case, energy is being both drawn and returned to the supply in each half cycle. This is termed reactive power. No work is done, the energy is simply cycling to and from the magnetic field in the inductor. Consider the following capacitive circuit with a 3-volt AC supply and a load of 1.5 ohms. By Ohm's law, this circuit will draw a current of 2 amperes. And since the load is purely capacitive, the current will lead the supply by 90 degrees. The power drawn from the supply at any point along the horizontal axis may be calculated by multiplying the instantaneous voltage by the instantaneous current. So between 0 degrees and 90 degrees, the voltage is positive, but the current is negative, so the resultant power consumed is negative with a peak value of 45 degrees. and between 90 degrees and 180 degrees, both the current and the voltage are positive, so the resultant power consumed is positive and has a peak value at 135 degrees. In this case, energy is being both drawn and returned to the supply in each half cycle. This is termed reactive power. No work is done. The energy is simply cycling to and from the electric field in the capacitor. Consider the following circuit with a 3-volt AC supply and a load of 1.5 ohms. By Ohm's law, this circuit will draw a current of 2 amperes. And since the magnitude of resistance is equal to the magnitude of the inductive reactance, the angle of the impedance will be 45 degrees, and hence the current will lag the supply by 45 degrees. The power drawn from the supply at any point along the horizontal axis may be calculated by multiplying the instantaneous voltage by the instantaneous current. So between 0 degrees and 135 degrees, both the current and the voltage are positive, so the resultant power consumed is positive and has a peak value at 67.5 degrees. Between 135 and 180 degrees, the voltage is positive but the current is negative, so the resultant power consumed is negative, with a peak value at 156 degrees. In this case, some of the power drawn from the supply is consumed by the resistive proportion of the load and is real power. The rest of the power is reactive power, which is energy cycling between the magnetic field of the inductor and the supply. The phase angle is defined as the angle between the supply voltage and the resulting circuit current. The phase angle may be determined by subtracting the angle of the supply voltage, theta v, from the angle of the resultant current, theta I. The highlighted box shows the phase angle is equal to theta I minus theta v. The current I angle theta I degrees can be considered to be made up from 2 components. The in-phase component, I times cosine theta, that will determine how much of the power drawn will be real power, and the out-of-phase component, I times sine theta, that will determine how much of the power drawn is reactive power. Up until now, we have been looking at the power drawn as a series of peaks. To determine the average power drawn by a load, we must work with the RMS value of both voltage and current, which by definition represents the DC equivalent value of the AC quantities. The real power is where the energy is used to do work, symbol P, unit watts. This is obtained by multiplying the RMS values of the voltage by the in-phase component of the current. The highlighted box shows that real power P is equal to the voltage V times the current I times the cosine of the phase angle theta. The reactive power is where the energy is cycling to and from the supply, symbol Q, unit volt-amperes reactive. This is obtained by multiplying the RMS values of the voltage by the out-of-phase component of the current. The highlighted box shows that reactive power Q is equal to the voltage V times the current I times the sine of the phase angle theta. The apparent power is the energy that is apparently being used if the phase angle is ignored, symbol S, unit volt-amperes. This is obtained by multiplying the RMS values of the voltage by the current. The highlighted box shows that apparent power S is equal to the voltage V times the current I. The term power factor is the name given to the cosine of the phase angle as shown in the highlighted box, symbol PF, and the units are dimensionless. This term is very significant as it determines how much of the power drawn from the load will be real power. Since the maximum value of the phase angle will be plus or minus 90 degrees, the power factor will always be a positive number, so it has to be quoted as a leading power factor for a positive phase angle or as a lagging power factor for a negative phase angle. Note, large electrical loads are usually rated by their apparent power S and power factor PF. For instance, a load of 10 MVA with a power factor of 0.87 lagging. The following example is in the accompanying workbook, AC Power, Power Factor. Here we are required to determine the power factor for a load when A, the phase angle of the load is plus 30 degrees. So, power factor equals the cosine of the phase angle. Substituting the values, power factor equals the cosine of 30 degrees, which equals 0.867 leading, as the phase angle was positive. In part B, the phase angle of the load is minus 40 degrees. So the power factor equals the cosine of the phase angle. Substituting the values, power factor equals cosine of minus 40 degrees, which equals 0.766 lagging, as the phase angle was negative. The three expressions of power, real, reactive, and apparent, are complex quantities, and their relationship to each other may be displayed graphically in a scaled power diagram or expressed numerically. In a power diagram, the real power, P or P plus J0, may be represented by a scaled line drawn on the horizontal. The reactive power Q, or 0 plus or minus JQ, may be represented by a scaled line drawn at the end of the real power line P, either vertically up if the reactive power was positive, plus JQ, or vertically down if the reactive power was negative, minus JQ. Finally, the apparent power S is the resultant of the real power P plus the reactive power JQ, represented by a line drawn from the start of the real power to the end of the reactive power. The scaled value of the line is the magnitude of apparent power. The angle from the real power P to the apparent power S is the phase angle, and the cosine of the phase angle is the power factor of the system. Using complex numbers, apparent power S angle theta equals the real power P plus the reactive power JQ. Or by trigonometry, as we have a right-angled triangle, apparent power S equals the square root of the real power P squared plus the reactive power Q squared. And the phase angle theta equals the inverse tan of reactive power divided by real power. The following example is in the accompanying workbook, AC Power, Power Calculations. Here we have been given a phasor diagram showing the RMS values for the supply voltage and the resultant current for a circuit, and we are required to calculate A, the apparent power S, B, the phase angle theta, C, the real power P, D, the reactive power Q, E, the power factor PF, and F, draw the power diagram to a suitable scale. Part A is to calculate the apparent power S. So, the apparent power S equals the supply voltage times the current. Substituting the value, apparent power S equals 100 times 2, which equals 200 volt amperes. Part B is to calculate the phase angle theta. So the phase angle equals the angle of the current minus the angle of the voltage. Substituting values, theta equals 50 minus 20, which equals 30 degrees. Part C is to calculate the real power P. So the real power P equals the supply voltage times the current times the cosine of the phase angle. Substituting value, the real power P equals 100 times 2 times cosine 30, which equals 173 watts. Part D is to calculate the reactive power Q. So, the reactive power Q equals the supply voltage times the current times the sine of the phase angle. Substituting values, the reactive power Q equals 100 times 2 times sine 30, which equals 100 volt amperes reactive. Part E is to calculate the power factor PF. So, power factor equals the cosine of the phase angle. Substituting values, PF equals cosine 30, which equals 0.866 leading as the phase angle was positive. An alternative way to calculate the real power P and the reactive power Q is to use complex numbers. So, apparent power S angle theta equals the real power P plus the reactive power JQ. Substituting value, 200 angle 30 equals P plus JQ. Using a calculator to do a polar to rectangular conversion, 200 angle 30 equals 173 plus J100. So for part C, the real power P equals 173 watts, and for part D, the reactive power Q equals 100 volt amperes reactive. Part F is to draw a scaled power diagram. To ensure that the diagram will fit on a page, I suggest using a scale where the largest value always equals 100 millimeters. In this example, the apparent power S equals 200 volt amperes. So the scale for this power diagram is 200 volt amperes equals 100 millimeters, or 2 volt amperes equals 1 millimeter. Using this scale, the length of each of the variables, the apparent power, the real power, and the reactive power, may be calculated. So the apparent power S equals 200 divided by 2, which equals 100 millimeters. And the real power P equals 173 divided by 2, which equals 86.6 millimeters. And finally, the reactive power Q equals 100 divided by 2, which equals 50 millimeters. The line representing real power P is drawn on the horizontal 86.6 millimeters long. Then the 50 millimeter line representing the reactive power Q is drawn vertically up, since this value is positive. Finally, a line is drawn from the start of the real power to the end of the reactive power, which represents the apparent power S. When this line is measured, it will be 100 millimeters long and be at an angle of 30 degrees to the real power line.